hours. I think we managed with 3, and the second reason is because I am unsure how much time we are going to take for the detection part and the classification, okay, which is the part that has been added in place of the 2D signals. Okay, usually in 2D I spend 1 week and a half, 2 weeks. So for this reason I left some buffer. Okay. Anyway, so today we talk about the spectral analysis. So spectral analysis, okay, is related to estimate the spectrum, so the distribution, the frequency distribution of the random process, estimated by a limited sample over a limited set of data. So that is, the spectral analysis goes, into this big chapter. And so, in estimating the power spectral density, it's easy if you know the autocorrelation because you make a Fourier transform. Okay? But in practice you don't, so you cannot measure the expectation. So this step is something that cannot be done in practice. Okay? The main reason is because I don't have an infinite number of observations, but I have a limited set of observations. So usually I have n samples. It's like for the homework, you have a limited data. And by the way, in the homework there are also non-stationary. Let's forget about that. Okay. So the spectral analysis has to do with a limited set of data and estimating the distribution of the power spectral density, assuming that the process is stationary, at least within the n samples that we are considering. So the goal is to estimate this guy, which is the Fourier transform of the autocorrelation of the random process. So rather than, usually we will see that rather than estimating the autocorrelation, the goal is that I estimated directly the power spectral density. So it's we can either write in this way or the other way. So we say that we have the estimate of the power spectral density with S hat, or we say that the power spectral density is dependent on a set of data. Okay. In this way, I highlight that the power spectral density is dependent on a limited set of data. So now, there are some way to approach. By the way, if you remember when I was illustrating the power spectral density of here, when I was running this code. Okay. That's one way, for instance. Okay, this is one code. Okay. Now this code is a code that is measuring the vibration, and I think there were some mechanics about it. So it's measuring vibration, so you can record all the vibration here, and then you can calculate the spectral properties of the vibration. So this is the MEMS of the accelerometer. Okay, so X, Y, Z. And then it's measuring the vibration. So you see, if I move in this direction, if I move in the other direction, okay, and if I move in the third direction, okay. So and you are pretty aware why Z is already, it contains already an acceleration, okay, which is is the Hertz acceleration, okay. So and if I look at some historic data, I don't know if it was this one. Let me see. This was just the vibration, but for instance, I can acquire, I can acquire vibration like here. And then what I'm trying to give a vibration which is approximately periodic, okay? And then what I expect is that, I expect that when I represent, so I acquired, I go here, this is Saturday, okay. So, you know, what I see here is the power spectral density of the corresponding vibration. This is the vibration phenomenon, okay? And this is the tilting effect. So it's almost close to 10 on the top. This is the ground and then, you know, the other vibration down. This is the raw data, okay? The raw data contains vibration on the z-axis, which is fluctuating over there. That's why, because I was hitting vertically. And this is the power spectral density. So the power spectral density highlights some resonance on the z component and on the other component, but you know, the dominant part is on the z component. So there is these, let me say, dominant vibration, then there are a set of other vibrations like you know, the harmonics. Okay. So if rather than hitting by my hand, I'm going to hit by hammer, okay, tung, 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 tung. Then you know the hitting is very strong, and then a vibration is not, let me say, is starting to touch the non-linearity of the system. And if it is a non-linear, so what I expect the fundamental component and then all the harmonics. Okay, so if you have a I mean the heating excitation which contains the harmonics, so the harmonics are helpful to understand what is the frequency of the fundamental. Okay, just in case. Now, if you ask mechanical engineer, aeronautic engineers, the study of vibration is crucial for them. For instance, you know, we were discussing yesterday afternoon about some possible tests that you can do in the air-wind room. You know, Polytechnic has this big air-wind, okay? And so, you know, you have a wind room that is, there is a wind that is, you know, it's floating at 200 kilometers per hour, and which is used by aeronautic car or by bridges to check about the statics, but also vibration there. And the bridge that collapsed in Genoa, okay? It's very much a sensor equipment to check if it is vibrating or not. So vibration is important. I mean, to conclude the story, you know, vibration is one aspect and is in front of every day, every person, you know, and it's important, okay? So in order to understand what is the distribution of power spectral density, you need to carry out the spectral analysis, okay? So now, going back to here, okay, so the goal is to estimate the power spectral density, which is the plot that, you know, we were showing with all the resonances. Now, there are two major methods to do that. One method is called non-parametric. So that means that the power spectral density is arbitrary, so is anywhere, okay? So that means that you don't assume any a priori information on the shape of the spectrum. Okay, you know, in jargon, the power spectral density is called spectrum. Okay, so you know that's a quite common jargon. So then we say that, you know, in a non-parametric method, I don't know the power spectral density, so I don't know the spectrum, the distribution of the frequencies. And the method which is used, this is the second column, is called the periodogram. So the periodogram is the method that is used when you don't know anything about it. It's a method that you do in the first sight. It's a method that I illustrated before. In the code, this code is made in the periodogram. This is a periodogram, okay? So it's representing the distribution of the different, let me say, power versus frequency component, okay? Because the periodogram is measured, power spectral density is measured in terms of power versus, you know, for any frequency being. Okay, so it's a watt watt per hertz or similar. Okay. So now going here, flipping back and going here. So the periodogram is the power spectral density that you do at the first sight. When you don't know what to do, you start with the periodogram. Okay. So periodogram, since a periodogram is by using the FFT or DFT, that means that we need to know a little bit deeper the properties of the DFT and FFT. Now, and this is something that we will do. Now, the other methods that we can implement are called parametric. Parametric means that the power spectral density, so the assumption here, this column here is the assumption or the model. Okay. And so the power spectral density for non-parametric is arbitrary, and the power spectral density for parametric is rational. So the power spectral density is rational. So, rational means that is represented by the ratio of two polynomials. Okay, so since the ratio of two polynomials is representing a finite difference equation, that means that we are assuming, so when I write in this way, I am assuming as if the power spectral density, in this case, has been generated by a white process filtered by a particular filter. So in this second case, it looks like if the xn, which is the data, has been generated, by an unknown filter, where I have a BZ and AZ as a z-tos form of the filter, excited by a random process. I don't know what I call, not W we use for the noise, what we call GN. Okay. So, and this random process, I don't care about what is the value of the GN, but what I know is that this has a power that is sigma squared. Okay. So according to that, this is sigma squared. So according to that, I am modeling the mechanism of generating my random process by a kind of a black box, where I know that inside in the black box there was a white noise, a white process filtered by a particular filter. Now, the key point is that if I know B, if I know A, if I know sigma square, I know the power spectral density. So then, we can customize, we can specialize this parametric model in three different methods. Okay, so we can characterize the parametric power spectral density estimation by an ARMA. An ARMA means that we have a polynomial representing the zeros, a polynomial representing the poles, and the scaling factor. So sigma square is acting as a scaling factor. We have the autoregressive, then the power spectral density, actually the estimated power spectral density, is obtained by, by only the poles. Moving average is obtained by only the zeros. So in this case, let me say, I need to estimate the coefficient, the cyclic coefficient B. In this case, I need to estimate the cyclic coefficient of the polynomial A. In this case, I need to estimate A and B. In all cases, I need to estimate the hypothetical, so the estimated excitation. Now, let me go back to our example, to the example before. Here, so if I look at here, what I see here, I see some, some resonance. Okay. So at one resonance, second, third, fourth, fifth, sixth, okay? Then you know it's decreasing. Now, so I took the data and then made the parallelogram, okay? This is the parallelogram. So after doing the parallelogram, I see these resonances. So what I can do, I can say, well, those resonances have been generated by a random process, which is called G, I guess, by a random process, which has been filtered by a filter 1 over AZ. This Z is a set of poles, depends on the set of coefficient A, okay? And this way I generate that XM. So since I have 6 poles, 1, 2, 3, 4, 5, 6 or so, okay? So that means that here I have 6 poles. Okay? So, you know, the goal is this. If I know the position of the poles, if I know the excitation power here, okay, so what I can do, I can estimate the polynomial or estimate the position of the poles. Okay? I know that there are 6 poles because I'm looking at the parallelogram, but you know, I might over parameterize the model, which means I can assign, make it this way, more poles than necessary. So, you know, what I do, I start with 6 poles, and then, you know, starting by 6 poles, I try to estimate the position of these 6 poles. This is the autoregressive spectral analysis, okay? So I estimate the position of 6 poles, or I estimate the set of coefficient A, which is the same, of the polynomial. I estimate that sigma, okay? So, I mean, the way I do is, you know, we will talk on that, okay? So assume that I have those set of coefficient A, and I have that sigma squared, okay? Okay? Then, you know, I know a system that excited by that sigma hat, and shaping the output by this filter with the coefficient A hat, okay, is giving me a power spectral density which is similar to the one that I'm looking for. Then I estimate my power spectral density using the parametric method. So this is how the parametric method works. Now, if you have data, you don't know the resonance, you know nothing about that. So you start with some data, and you know, which is typically the case. I mean, if you know that I don't know, you have a airplane and the vibration of the structure has some resonance, then I mean, you can impose the frequency of those resonance. If you don't know that, then you know you don't impose it, and you search for that. Okay. So finding the roots in this case, which is finding the poles, you can estimate the frequency of resonance for any structure. Okay. Now, as you see, you know, the parametric method is totally different from a non-parametric one, which is not assuming any model. The parametric one is assuming the model. Now, since, for instance, in this case, since the model is by using only poles, so what I expect, you know, approximately, what I expect is that if I put my poles, I don't know, if it comes and my poles is made in this way, which is as a specular one. Okay. So this is the distribution of the poles that I get. Okay. Now these are the poles of AZ. Then you know that I have the complex conjugate which goes on the other side. Now what I expect that the power spectral density is approximately, these are the position of the poles. This is number 1, number 2, number 3, number 4. Okay, and then you know I have the friends on the other side. Okay, so my power spectral density that I expect in this case is represented by a set of peaks. So look at this one, okay? The other is exactly the same. So you know what I expect? I expect that my power spectral density that I'm looking for is represented by a set of resonances, okay? This is the typical shape of power spectral density that I get by autoregressive spectral analysis. Now, if by using the periodogram, so making the test that with the vibration that we did, and for some reason my periodogram is finding something that is something like that. Assuming that I make a periodogram. And by the periodogram, I get this behavior. So this behavior shows me that here is going to 0, okay? Then, if I try to use the autoregressive spectral analysis, the autoregressive spectral analysis is shaping approximately this way, and is not capturing the 0. So to capture the 0, if I see that in periodogram I have a 0, then I need to put a 0 in my model, which means that I need to do the ARMA spectral analysis. Okay? So there is a 0 somewhere in between. Assume it's similar to that. Okay? Then I need to make a ARMA spectral analysis. Now let me tell you one spectral analysis is an art. Okay? So which means that there are people that are expert on spectral analysis. Okay? There are people that they get the data, manipulate, make the periodogram, is going flipping back, going to the parametric spectral analysis, increasing the order, putting the 0, removing one pole, until finds the best parametric representation. Okay, it's a job. Okay, it's an art. It's an art. And then my goal is not to tell you how is the art. My goal is to tell you what are the main conceptual steps that the guy that is the owner of this art makes in order to proceed to make the steps in estimating the power spectral density. And by the way, even if I can say that the power spectral analysis is an art, and if I said 20 years ago, that means having different codes, running different codes. Now you have a MATLAB, so it's just one code. So you run one code, you go back, you iterate, and so on. Okay. Now, let's review a little bit something, okay? So it's not necessary, but let's review. So you remember that if it is a stationary, the mean is not dependent on the position of the time. We have the autocovariance, okay? The autocovariance is represented by the covariance between xn and xn plus k. And autocorrelation sequence is the expectation xn plus k. If complex conjugate, it goes a star there. By the way, we know that the autocorrelation and the covariance, they are linked by the mean. If we are assuming as it is carried out by 99% of any application. If you are assuming that it is zero mean because you remove the mean, because you process to cancel the mean and so on, see the homework number 2. Okay. So if you have something similar, then you have the equality between the autocorrelation and the covariance. And the covariance, has some particular. Furthermore, okay, we know that the power spectral density, okay, is a Fourier transform, which I can represent in this way, but I can represent as we do here, as x omega. Okay. So it's the Fourier transform of the covariance, and if it is zero mean, it coincide with the power spectral density. Filtering. Okay, so by the way, this is we discussed about that. Okay, so you have it. About where the poles are coming, where the zero are coming. Okay, I don't know. There's nothing to really discuss because we already touched it. So, I mean, this is the schematic of having a system where you have a random process xn, which is filtered by filter h with impulse response hn, and yn is the output here. And the filter is represented by a linear time invariant system, and if the filter response is the response of a linear time invariant system, it can be always described by a finite difference equation. Okay. Now this finite difference equation, I can apply the z transform left and right. Okay, and this is what I get. Okay. So, yeah, so this was more or less we have been already discussing that. Yeah. Okay. Now let's start with one aspect that we never discussed. How to estimate the autocorrelation. Okay. Now, if I need to estimate the autocorrelation, because I mean everything is the mother of everything is the autocorrelation, because the power spectral density is the Fourier transform of the autocorrelation. So, first of all, I need to have a very good control of what is the sample estimate of the autocorrelation. Now, the sample estimate means that I have a set of samples, okay, which are representing my file, my data. Okay. And then I can define the sample estimate of the autocorrelation, which is a cross x-core, right? X-core. Okay. What x-core does? If you give to x-core the same data. Now, if you go to the help of x-core function, you will see that in the help there is biased or unbiased correlation. Now, what does it mean? It means the following. Let's start with this. Let's start with the sample estimate of the autocorrelation. And I'm using these formula, which is x star n plus k, which is similar to that. So how this one is acting? This one is taking xn, now I have xn, and then I have xn plus k. So that means that I have a certain amount of data, and so this one is xn, and this one is xn plus k, okay? Because it's a shifter on one side. Now, looking at what the formula says is, you need to take xn, x star if you like, okay? X star n, and xn plus k, and then multiply each other. Now, when I multiply each other, these two shifted versions of the same sample sequence, which means our current data, they overlap only within a certain limited portion. It's not fully overlapping. It's only overlapping in the center. Now, these particular sample estimate says I'm summing all divided by n, and n is the length of the data. Now, when I want to understand if this sample estimate is correct or not, the way I do it is by applying the expectation. And first of all, I want to see if this sample estimate is biased or not. Because that is, if you remember, every time we have an estimator, I check the bias and I check the variance, okay? So, I start checking the bias. So I want to see what is the bias of this estimator of the autocorrelation. Now, looking at the bias, what I can see is that, taking the expectation here, the expectation goes inside in the sum. Okay. And so, going inside in this sum, then, I'm taking the expectation of, of x and xn plus k. So taking this expectation is giving me exactly the autocorrelation. But, I'm only summing a subset of data. And exactly the amount of data that I'm summing, so this overlapping region, is represented by n minus k. So, and since I can shift in one direction and the other direction, the overlapping part is n minus absolute value of k. So, for this reason, since here I also have a division by n, so, the applying the number of samples that are overlapping, which is n minus k, divided by n. So what I can find that, the sample estimate of the autocorrelation is biased. Okay? Because, this number is not equal to 1. Unbiased would be that this one is equal to 1. So this sample estimate is biased. Okay? Now, let me look at very carefully that. Now, if I look at very carefully, I have a double screen. So, looking at that equation says I have expectation of r hat x k is equal. Now I rewrite in a slightly different way. It is 1 minus absolute value of k divided by n multiplied by rx k. Okay. Now remember, this is the sample estimate, and this is the true autocorrelation. Okay. Now looking there, there is a window applied to the true autocorrelation, and the window is triangular. So this one is equivalent to have the autocorrelation, sketch. Okay, this is the autocorrelation. And this autocorrelation is window by a triangular window that goes between minus n to n. So that means that the bias is given by an implicit windowing by a triangular window into the autocorrelation. Now, this window will play a role later. Okay? Now, so this is the window. Now, let me call this window W. Okay. WB. Okay. Which is Bartlett or triangular window. So it is the multiplication about this W, the RK, the true autocorrelation with this WK. This W, so this window is truncating the autocorrelation to plus minus n because I have a limited data n. No, but since I'm not happy with this bias, because I have been teasing you so much as saying, try to avoid the bias, try to avoid the bias. Okay, so what we can do, we can write an unbiased estimate of the autocorrelation. So the mistake we did here, which is not a mistake, but it's a one estimator. So you remember, I can declare anything as an estimator. So what I did here is that this is an estimator. Okay. So then once I studied that this one is biased, then I can reconsider the estimator, and then rather than dividing by n, as I did here, I can divide by the effective number of samples that are used in calculating the sum of the product of the two sequences, one shifted k samples with respect to the other. So since the sequences are shifted by k, then this is the overlapping region. Okay? So n minus absolute k is the overlapping region. Now, defining a new sample estimate of the autocorrelation, which I call R tilde, then defining this way, then when I calculate the expectation, the expectation now is perfectly unbiased, up to n. So that means that in this second case, the expectation of R tilde x k is equal to so it's equal to Rx k for any k within n and then is 0 elsewhere. Okay. Now, what does it mean? It means that in this case, it is similar to the previous one, except that I am applying a rectangular window. Okay? Because this says that it's equal to that up to that one, and then it's 0. So it means that it is equal to the true one up to here. Then 0. Okay? So what does it mean? It means that, rather than writing in this way, I can write as Rxk multiplied by I call later R. Yes. R. Okay. Okay? A rectangular window. Now keep in mind about that. And this is the rectangular window I'm applying. Okay? And minus 1 to n minus 1. Okay? That's a rectangular window I'm applying. So when I estimate my autocorrelation, there is an implicit window. Now this implicit window is not, the window is a consequence of the limitation of the length of the sequence. I'm not windowing. It's due to the fact that the sequence is limited in length. Is n. Now, but since the power spectral density is the Fourier transform of the autocorrelation, then I can calculate the Fourier transform of the biased estimate and of the unbiased estimate. So let's compute it. So as I said, I can calculate the Fourier transform here of these two estimates, so the unbiased and the biased one. It's simply the Fourier transform. Okay? And then, what I can do is I can calculate the expectation of these Fourier transform, where the expectation here is with respect to the only random value, which is x. Okay? Now, when I calculate the expectation here, the expectation is the expectation on that multiplied by the Fourier transform. Then, I have the rectangular window on one side and I have a Bartlett or a triangular window on the other side, multiplied by R. But, that means that it is equal to the Fourier transform of the rectangular window convolved by the power spectral density, or the triangular window convolved by the power spectral density. In other words, if I make it this way here, now I cancel the two implicit window. I need a little bit of room. So if I calculate the Fourier transform this is equal to the Fourier transform of a backplane of a separate triangular window convolved, because you know, the product becomes a convolution. Okay. Convolved with the Fourier transform of the autocorrelation, which is the power spectral density. And similarly there, I have the Fourier transform of rectangular window convolved by the power spectral density. Now, so let's see what is the difference between the two. Now, in the first case, I'm computing the first one. I'm computing the Fourier transform of triangular window. You know that a triangular window or a triangle is obtained by a convolution of two rectangles. Okay. Then that means that the Fourier transform of a rectangle is a sinc. So when I make in the Fourier transform, this is the sinc multiplied, because in frequencies product, multiplied by a sinc. So the Fourier transform here is a sinc square. Okay? So this is sinc square of some omega. So there is something. Here, I have a Fourier transform of a rectangular. And then this one is, the Fourier transform is a sinc. So what I notice from that is that the sample estimate of the autocorrelation, which is biased, is giving me the Fourier transform, which is the convolution between the sinc square and then the true power spectral density. By the way, this is what I'm looking for. But it's too early. I'm putting some easy concept on the ground. Now, due to that, that means that this frequency transform is the true power spectral density. I don't know. Imagine that the true power spectral density is this. Convolved by a sinc square. Okay. Now if I convolve by a sinc square, what's happened is that by convolving, at least the result of the convolution is always positive, or at most it can be zero. So what I can write here, I can write that the results of this convolution is positive semi-definite, so it's larger or equal to 0. In the second case, I need to convolve the power spectral density with a sinc, which is positive and negative. So when I convolve this with that, it might happen that the results of the convolution, it might be positive and negative. So going back to the point, in this case, the results might be larger than 0 or might be lower than 0. So having a Fourier transform of the autocorrelation that contains the Fourier transform, that contains values that are positive and negative, makes the corresponding Fourier transform meaningless for the usage of a frequency of the power spectral density estimation. It's useless because, this one is giving you a power spectral density that is positive and negative. And having a negative power makes no sense. So because of that, even if R tilde is a sample estimate of the autocorrelation, which is unbiased, it is useless for our purpose. Okay? And by the way, this rule is telling us something. It's telling the following. If I have the autocorrelation, assume that someone is giving you the autocorrelation. Assume that you know the autocorrelation. Assume that for the experiment, I don't know, there is a genie that is giving you the autocorrelation. It's God which is giving you the autocorrelation. Okay? And then you want to calculate the power spectral density. But I mean, since the autocorrelation is too long, okay, so I give you the autocorrelation. Okay. Then you want to calculate that. But you want to calculate by the Fourier transform. I mean, you have your computer. You want to calculate that. And so what you do, you truncate. Okay? Now, if you truncate as it is, which means you truncate, what you might get that the Fourier transform has a positive and negative values. So in spectral analysis, you need to be very careful how you truncate your autocorrelation. If you truncate sharply, you might get a corresponding Fourier transform, which is what we call the estimate of the power spectral density, that might have values that are positive and negative. Having negative power means that you have a signal, and in this signal, okay, measuring the power in every band. So it's like, you have in band, in 1 hertz, you measure the power. What is the power in hertz 2, in 3 hertz, in 4 hertz? Then at a certain point, the power is negative. So it means that, you, rather than the signal is giving you the power, you need to give the power to the signal, which makes no sense. Okay? So, that is, this is what the timing. So to summarize, I'll summarize here so it remains. Okay, this is what we did. Let Rxk be known. Be aware on the way we truncate. Okay, because if you take Rxk, which is and you want to limit, I don't know, for some reason you say, oh, look at here. Before and after this point is fluctuating, it's close to 0. Then you know what? I simply truncate. So I cut it out, this and that. So, I decide that I want to keep only this one. Okay? Now, if you decide to keep only that one, then you would be implicitly saying that you extract only those signals. Right? Now, when you extract those signals, you are truncating because you are assuming that everything else is 0. Okay? Now, if you extracted that signal, never extract as it is. So never make the direct assignment. Do it by windowing. So you need to do it by a window. So you need to make it, you need to multiply by a window in such a way that you get, Rxk, which is after, after limiting within a certain window, in such a way that the Fourier transform of R not K which is equal to the Fourier transform of W K convolved by the power spectrum density. This Fourier transform should be positive semi-definite. This is how you should do. So if you make it by a rectangular one, if you simply copy, that's what I'm saying, you know, a very stupid operation, copying. I copy just a piece of data. I segment, okay? I decide to segment my autocorrelation in such a way that I extract only a piece. Don't do that. Don't do this, just the extraction directly. Pre-multiply the data. You know, in one possible window, okay, so one option is to smooth, so take a triangular window. Don't extract as a rectangular one, okay? Now, this concept will be very important when we deal with the moving average and the spectral analysis, but you know, and also the related exercise. But you know, I want to start seeding this concept, okay? Now, going back to this point, now you know, we have seen that this is not preferred, as this one is larger or equal 0, so it's not what we want, and this is larger or equal 0, so that is the one that I prefer. Now, the further information is the following. What's happened if, you know, what we have seen is that because my power spectral density is convolved by a sink. This is a sink. Now, you know, in this estimate is in some way is biased. Okay? So the estimation of the power spectral density carried out in this way is biased. It's biased because I mean I have these sink which is convolving the power spectral density. Now, the good news is the following. If I take a triangular window, and I take the triangular window such that n is going to infinity, so you know I have a triangle, and this triangle is getting bigger, 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 bigger. Now, the Fourier transform is getting smaller, 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 okay? Now, for n going to infinity, or large enough, then you know what's happening is that you know my window is negligible, my Fourier transform is delta-like, and my bias goes to 0. And so we can say that is asymptotically unbiased. Okay. Now, let's start with the periodogram. Now, the periodogram is the power spectral density estimator that are mostly used. It's mostly used because it's easy. It's stupid, it's trivial, but as everything, you know, I hope you learn, mostly by homework and workshop, probably you learn that everything that is stupid, if you don't take all the care to everything, you never go anywhere. And so, you know, you need to be very careful to what you do. So, what I'm saying is that, what is the periodogram? You know, I mean, reading the definition of periodogram is, let me say, trivial, okay? Now, what is that? The periodogram is I have a sequence, so remember, this is the experimental sequence, so it's a sample sequence, so it's the data, okay? Then I calculate the discrete Fourier transform, so omega k is calculated on 2 pi k divided by n. So you make this one is the discrete Fourier transform calculated on for x calculated for omega equal 2 pi k divided by n, okay, which I indicated as omega k. So it's the discrete Fourier transform square, well, square, you know, is the energy, yes, that's fine, divided by n, okay, finish, that's it. So since the FFT is fast, then, you know, everybody's using it, okay. Now, that's a good news. The good news is that, you know, it's simple. It is the DFT to the square. Okay? That's what the people say. It's the DFT to the square normalized because I divide by n. Okay. If you know, if I want some particularity, I also can skip the division by n because if I'm doing everything by the same size, then no, it's not necessary because they are comparable one with respect to another. Now, that's the good news. The bad news. The bad news number one. The periodogram. So the expectation of this estimator is this one, and the periodogram is biased. Is strongly biased. Is severely biased. Is biased by the conversion of a sink, of a periodic sink. So this is the true one, and this is the bias effect. This bias is asymptotically unbiased when I take n going to infinity. Yeah, but you know, I have n going to infinity, so I don't need to make the periodogram because I mean I can calculate everything exactly, okay, assuming the stationarity. So I mean, everybody can do everything if I has an infinite number of samples. So the challenge is not that you have an infinite number of samples. It's not that, you know, I mean, you want to create an engineering solution by having an infinite budget. I mean, the challenge is to create something having a limited budget. And here the budget is the size of the sample. So that means that we need to understand how to handle this bias. Then, the second bad news is that the variance of the periodogram, do you remember, you know, the power spectral density is a deterministic quantity. This is something that, you know, is probably confusing you a little bit. Because, I mean, the power spectral density is a deterministic quantity, it's not random. What is random is the signal or the random process that I'm using. So I have a random process, but this random process has a certain power spectral density. So the power spectral density, okay, is deterministic, so it's a function. Okay? So being a function, the power spectral density, okay, is a quantity that can be estimated by a non-Bayesian estimator. Because, you know, the power spectral density has a certain shape. Look at it on the top. That one. You see? It's going that way. That is the behavior, is the power spectral density. So it's the behavior of the power spectral density versus frequency of a random process. But, you know, it's the process that is random, but the power spectral density is deterministic. And I can parameterize by poles, by zeros, by the power n. A power is deterministic quantity. If I need to estimate the power of something, I'm estimating a deterministic quantity. So I'm using a non-Bayesian approach. So as we have seen with the non-Bayesian approach, we have been always computing the bias and the variance. And so here we compute the bias and the variance. And now, looking at the bias, you know, we have that the periodogram is biased. Then, looking at the variance, now the variance of the estimate is the parameter to the square. Now, just to tell you what does it mean. Now, assume that, I want to estimate how many cookies are in that pack, okay? Now, how many cookies, okay? So I give you, you write your estimator, right? Now, what about if your estimator has a variance that is the square of the number of cookies? So which means, if inside there are 10 cookies, the variance is 10 to the square, or the standard deviation is 10, which means you are estimating 10 cookies, but is 1 plus minus 1 standard deviation it's going from 0 to 20. Okay? I mean, this estimator is very bad if you think about it, So having an estimator that has a variance that is as much as the quantity that you want to estimate to the square is a very bad estimator. So, concluding here, we have a bias power estimate of the power spectral density, and then, it has a variance that is very big. So, I mean, we are better to, I don't know, if we keep discussing here, we are better to get the coffee, I mean, discussing about an estimator which is biased and so strong, and then, it has the power spectral density that is a square of the power itself. I mean, it's better to give up, really, okay? So, now, my goal is this. Let me illustrate the bias. Okay, I started discussing about the bias, and then and then I show you how to cope with the bias after the cookies, because I have a strong attraction about this bag. Okay. Very strong. Now, first of all, I like this board, it's big, so rather than writing there, I write here, and it's has more room. Okay, so let's read the bias effect, okay? Now, the way to compute the bias, this is one of, let me help you. What is written here? Here is written that the bias is the power spectral density convolved circularly to the sink, the periodic sink. Now, but look at that, omega is not a discrete. Okay. So on the left, I have the estimate of the power spectral density by the periodogram in the frequency omega k, where omega k is 2 pi k divided by n. Okay. So, and here I have the periodogram, I have the power spectral density, which is defined on the continuous omega. So, I first get the power spectral density. Second, I get the sink. Third, I convolve. Fourth, after convolving, I'm not here, I'm not joking, it's because it's about some of your exam. So after convolving, okay, is the exam when you make the written exam. After convolving, you sample. So this formula is saying, if I ask you, what is the bias of a periodogram? The bias of periodogram is, I can analytically compute by getting the true power spectral density, getting the sink, convolving, step number 3, after convolving, not before, after convolving, after step number 4, you sample. Okay? You sample. Now, let me make an example. Let me make a very simple example. imagine that, you know, we have an ideal low pass power spectral density, which is up to omega, which B, no, B, let's call omega naught. Okay, minus omega. This one that I'm representing, let's go up to 1. This one that I'm representing is the true power spectral density. Step number 1. I get the power spectral density, the true one. Okay? So in order to understand what is the bias analytically, I need to get the true power spectral density. Perhaps I know. Perhaps I know for some other reason. Second, get the sink. The sink is the periodic one. No, let's read the sink together. What is the maximum value of this periodic sink? Now, the maximum value of this periodic sink for omega going to 0. Now, this is n squared divided by n. So the amplitude of this periodic sink is n. Is 0. It's not a sample, it's just a value. What is the position of the zeros? Because there is a, you know, there is a repetition of zeros. By the way, that's a sink square. Okay, so that's the reason why I put this way. Okay. Now remember, if it is a sink square, okay, look in there. You know, a sink is going this way. The absolute value of a sink is going this way. A sink square is going this way. Okay? So this is a sink. This is absolute value of a sink. This is a sink square. You see, it's a difference here. So when you sketch a sink square, and you plot, you represent graphically without this smoothed part, I get the impression that you are not representing graphically a sink square. Anyway, so this is the sink square. Now, where is the zeros of this sink square? Then, you know, in order to understand where are the zeros, so what I do, I need to take a sine of omega and divide by 2, and then I need to find the zero of these sine omega and divide by 2. Now, you know, so that means I want to find when this one is equal to 0. Okay? So this is a sine. Huh? Then, you know, this is 0. Okay, so a sine is 0 when the argument is multiple of pi. Okay, except 0. Except 0 we already computed. So that means that omega n divided by 2 is equal to n times pi, where n is different from 0, because 0 is the kind of degenerate case which I already computed. Then, you know, that means that here, so I have omega, which is equal to 2 pi divided by n, capital N multiplied by lowercase n. So these are the position of the zeros. Okay? So starting with the first 0 is in 2 pi divided by n. The second 0 is 2 times 2 pi divided by n. The third 0 is 3 times 2 pi divided by n. And similarly to the other side. So the zeros are spaced apart 2 pi divided by n. Okay? These are the zeros of the sink. I'm only characterizing the sink. Then, step number 3. Clear? Step number 3. What I'm doing is, I'm computing the convolution. But you know, the convolution is circular because, I mean, I have a periodic sink, and then, you know, that one is periodic as well. Okay? So I need to compute the periodic convolution of the period 2 pi. Just keeps going. Okay? This is step number 3. So I need to calculate in a continuous way. It's not discrete. There's nothing discrete now. It's in a continuous way. The only place where I remember the size of my data is by the sink. It's by these periodic sink. This is where it goes of the limited size of the data. Nothing else. Now, when I make this convolution, you know what's happened by computing the convolution. Then, let me try. I try to sketch it. Okay? Then, you know, what I get something which is similar to that one. And, you know, it's similar to the other way. Positive, eh? All positive. Okay? This one is the convolution. And this axis is omega. And is limited between minus pi and pi. I'm not finished. I'm not finished. After doing this step, after computing the convolution, I am sampling now. Okay, I am sampling. So, sample here, sample there, sample there, sample there, sample, 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 and so on. Okay. After that, I'm sampling with a spacing that is 2 pi divided by n, which is the period of sampling interval is 2 pi divided by n. Now what is clear? I mean the procedure, I made like an elementary school, you know, okay? That's because I made it slowly, that's because, you know, this is where you made messy. I've seen everything on that. Okay, so 20, 30 years I've seen everything. But you always surprise me, so you know. I cannot illustrate all the cases. Okay, after doing that. Now, what I noticed is that by making this convolution, it comes this ripple, okay? Now, this means that here, where the true spectral density has no power, I might have a power. This is due to the way the parallelogram is computed. I say it again. In the places where, because I choose my power spectral density to be ideal, okay? So it's an ideal low pass power spectral density. And now, you know, because of this ideal low pass power spectral density has no power for omega, I mean for a frequency larger than omega naught, then you know, I mean, what I expect is that by the parallelogram, I expect no power here. But because of the convolution by the sink, it comes out that there are some powers there. That's a bad news. So that means that, you know, if I need to use the parallelogram, I need to be very careful. Because where I do not expect the power, I might get power. Drawback number one. Drawback number two. Here, you know, you look at here. You have a very sharp discontinuity. And here, the discontinuity is very smooth. So you have a transition. Okay? So this is what in electronics is called selectivity. So here you have a very high selectivity. Here you have a very low selectivity. Selectivity is the ratio between the interval, the frequency interval, when I go from 1 to 0, which is 0 in this ideal case, divided by the omega, where, you know, it's the transition frequency. Okay, omega naught. So here the selectivity is infinite. So, you know, it's an ideal. And, you know, because the selectivity is infinite, this is another reason why a low pass, ideal low pass, is impossible to implement. Okay? So, but on the other hand, when I make a parallelogram, I'm losing this high selectivity. So the parallelogram has the second drawback, which is smoothing me this sharp discontinuity. Okay. Now, let's make an example in this case. Let's assume that I want to use all this procedure, okay, to estimate a very small signal sinusoid which is there. There is a very small sinusoid here. Okay? Very tiny sinusoid here. Now, I put the sinusoid on the transition point of the power spectral density of that one. Now, we can call this one as a noise, and we can call this one as a signal. So perhaps, I don't know, this very low periodic signal is the engine of a submarine, for instance. You put a set of hydrophones to measure the engine of the submarine. Now, you can listen to that, right? Now I put it there. Okay? Now, you know, that means that because this transition is losing the selectivity, I mean, my small sinusoid is disappearing. So I cannot see it. So my goal is to see this sinusoid. Okay? And we will see after. We will see after. Okay? Now, to conclude, before that, this is my goal, right, today. Okay, my pleasure. So before that, let me say, you know, the variance is that one. Okay, is it clear? So the variance is really big. I mean, since the variance is this big, you know, I mean, it's useless. Because, I mean, having an estimator that has a variance as big as the quantity itself to the square makes the estimator totally useless. So, but the people are using the parallelogram, and then let's enjoy it then, you know. Okay.